Thank you for joining to this webinar. My name is Mikhail Magim. I'm civil engineer, and today's my webinar is about modeling of reinforced concrete structure using Midas FEA software. You are watching this webinar using GoToWebinar system, and at the end of webinar, when I will finish my presentation, you can ask your technical questions, and I will answer it. And question you can ask using chat window in a GoToWebinar dialog. On this slide, you can see the contents of what will be discussed today. The purpose of the webinar is to give you main recommendations about how to define nonlinear properties for concrete and reinforcement, how to create finite element model correctly, how to perform iterative analysis, and how to read and understand results obtained from analysis. So, as you know, nowadays, finite element method is a basis of computational tool, which can be used to simulate the response of any kind of structures, components, materials, when this structure is submitted to a specified load. Finite element method is extensively used to estimate the behavior of concrete structures. And to consider concrete in finite element model in practice, we usually use different assumptions and simplifications. In order to predict with high accuracy the behavior of concrete structures, appropriate constitutive model must be used. In practice exists two the most used models of concrete fracture in terms of finite element method: the discrete model and smeared crack model. The discrete model is especially suitable for simulation where the failure is governed by occurrence of a small number of cracks with a crack that has path that can be clearly predicted. Discrete crack modeling create cracks by means of separation of element H. In order to make this separation, an interface elements at the discrete crack location can be used interface elements. Also, you can use a XFEM model that allows you automatically consider crack initiation and growing. The discrete crack approach gives quite realistic results, but it's complicated to implement in real design practice. It's mostly used for scientific research. In smeared crack model, the fracture process is initiated when the maximum principal stress in finite element exceeds its tensile strength. The crack propagation is mainly controlled by the shape of tensile softening diagram with the fracture energy. And this approach is quite suitable for analysis and design of civil structures. And this approach is widely used in practice. In Midas FEA software, this model is implemented as total strain crack model. And further in my presentation, I will focus on this model. On this slide, you can see the uniaxial stress strain diagram for concrete tensions that are recommended for finite element simulation. It's preferred to use exponential softening type diagram. According to this diagram, during the tensioning, the concrete has linear behavior up to the limited tensile strength, and after that peak begins crack opening and the finite element stiffness reduced. After the reaching of limited strain of this diagram, assume that the general crack in the element is totally open, and in terms of finite element, the stiffness is zero and element doesn't work anymore. In Midas FEA, to describe this diagram, you have to define tensile strength of concrete, tensile fracture energy, and crack bend width. I will talk about these parameters a bit later during this presentation. In case of concrete compression, the parabolic diagram is preferred as it gives quite accurate results. According to this diagram, after the reaching of compressive strength of concrete, begins the crack softening, and this softening is based on compressive fracture energy. After the reaching of limited strain of this diagram, assume that concrete is crashed, and in terms of finite elements, the stiffness is zero and element doesn't work anymore. And Midas FEA, to describe this diagram, you have to define compressive strengths of concrete, compressive fracture energy, and crack bend width. The crack bend width is equivalent length, is an essential parameter in constitutive models that describe a softening stress-strain relationship for compression and tension. Typically, this length is equal to the length of finite element, but also you have to presume the expected crack orientation in the element. And then based on this, you may define the length properly. Also on this slide, you can see some recommendations about this equivalent length. In total strain crack exists two types of orthogonal crack models. It's a fixed and rotating. During the iterative step analysis of reinforced concrete structure, in finite elements, the direction of principal strains usually changes. The first crack is initiated based on the direction of principal strains. Using fixed approach, the crack direction remains unchanged with the changing of principal strains. Using rotating crack approach, the direction of crack is changing based on the changing of the direction of principal strains. In this case, if you are using a fixed crack approach, for analysis convergence, you have to consider retention factor for element shear stiffness. And this factor can be constant, variable, or you can define a shear stress strain diagram for this. It's quite difficult to recommend to a certain value of retention factor and approach to shear stiffness reduction of finite element, because it's mostly based on structure type and its behavior. But based on the analysis of some of the experimental tests of beams and slab fractures, this factor is between 0.05 and 0.3. Also, if you make comparison between rotating and fixed crack, in some cases rotating crack produces a lower strength that it should be, but at the same time rotating crack approach gives quite realistic crack pattern, especially in case of shear failure. So for conservative results, if you're working with a beam and slabs, I recommend to use a fixed crack model with a constant retention factor. Occurrence of crack in one direction change concrete compressive strength in opposite direction. This effect can be met, for example, in pre-stressed structures with the cracks in compressive zone or in columns. And Midas FEA can consider this effect automatically, use reduction factor due to the lateral cracking. Also, Midas FEA can consider automatically the increasing of strength in confined compression. Here, program during the analysis consider triaxial loading, medium and low lateral confinement. For reinforcement steel, the elastoplastic material model with or without hardness should be used. In Midas FEA, it's possible to keep finite element of reinforcement inside finite element of concrete without convergence of nodes. Program automatically applies the rigid links between the nodes of reinforcement and surrounding concrete nodes. Instead of using rigid links, you can also use elastic or inelastic links. And using an elastic link, it's possible to consider slip between reinforcement and concrete. Now I'd like to talk about materials. It must be used from design code to consider them inside Finite element software. For serviceability analysis, we use characteristic values of materials. And for failure, ultimate limit state must be used 3 types of parameters. It's a characteristic, design, and mean values. In the next slides, I will explain this. And here on this slide, you can see material properties for concrete. From this table, you can see formulas for calculation of tensile fracture energy and compressive fracture energy. And you can see that compressive fracture energy is based on the tensile fracture energy. Here are the material properties for reinforcement. Now, ultimate limit state. In nonlinear finite element analysis using Eurocode2nd, you can obtain a design resistance of structure by selecting one of 3 ways. According to the first method, the first way is based on the global safety factor. According to this approach, when you create a finite element model, for finite elements, you apply mean mechanical properties for concrete and for reinforcement. Then you perform analysis. After analysis, you estimate ultimate load, and you have to divide this ultimate load by global safety factor. And doing this, you will get design resistance. The second method is based on design properties. So when you create your model for finite elements, you apply design material properties and perform analysis. Once analysis is done, the ultimate load that you receive from analysis will be the design resistance. And the last method is based on coefficient of variation. According to this, you have to save your model into 2 files. In the first file, you find elements, apply mean mechanical properties, and perform analysis. In the second file, for your model, you apply characteristic mechanical properties and perform analysis as well. After the analysis of the second model, you can obtain coefficient of variation. And using this and results from the first file, you can calculate design resistance. It's up to you to select the appropriate method, but if you are not sure, you can perform with these 3 methods and select the lowest design value. But the second gives quite conservative results. Serviceability limit state. In this case, you have to make stress check, crack opening check, and deflection check. All necessary information can be obtained from the software. So in Midas FEA, at any point of your model, you can see stress in concrete. You can display a contour vertical displacement in a beam and check with the limited displacement. As for the crack opening, here, according to the total strain crack model, a program can give you a crack width as a product of principal tensile strain in a cracked finite element and a crack band width. Alternatively, you can use design approach. According to this approach, you have to calculate average stress in reinforcement. Program can give you this value in reinforcement, and you can roughly estimate the crack spacing. Now I would like to go through the benchmark test. And from this benchmark test, you will see the main principles of how to create a finite element model and make post-processing results in Midas FEA. Also, you will see comparison of crack pattern and capacity from numerical analysis and experimental test. All information about the experiment was taken from the thesis described on the slide. And according to the experiment, the object was destroyed due to the shear failure. As for example, here we'll consider a simply supported beam with a 3-point bending. The span of beam is 3 meters and height is half meter. This beam has 6 layers of reinforcing bars. Properties of concrete and reinforcement you can see in tables. Concrete compressive strength is 37 MPa, and average yield stress of reinforcement is 480 MPa. A constitutive way to calculate this benchmark object is to consider 2D plane stress model, because this beam has flexure only in one plane, so not necessary to consider solid elements here. In addition, I will consider only half of the model, as this object has a symmetry. On this slide, you can see some recommendations on meshing of the model. So if you work with 2D model, at least 6 elements over the head should be used. As for finite element, it's recommended to use rectangular element with a nonlinear shape function with a middle side nodes. Also, the mesh size can be submitted based on your proposal. For example, if you wish to get more detailed contour of cracks, the size of elements should be quite small. In my case, I will consider element with a length of 70 millimeters, and this length will be the crack band width as well. Reinforcement in the model defined as embedded truss element. If it's a truss element, you only have to define the area of reinforcing bars. For each layer in my model, I defined the total area of bars. For reinforcing steel, the bilinear and ideal plastic sustain diagram was used. For concrete, total strain material was used fixed crack model with a second stiffness. Also, I will consider rotating crack model for comparison. If you're working with the 2D models, you should use a second stiffness. If you need to consider a lateral crack effects and confinement effects, you also can check this. As for the tension behavior, the exponential software was chosen with a predefined tension strength, cracking energy, and the size of finite element. As for compression, used torrent field model. According to this model, you have to define only compressive strengths. Midas FEA inside has algorithms that can automatically describe the parabolic diagram based on only compressive strengths. And as for shear stiffness reduction, use constant beta factor 0.05. Now boundary conditions and loading. It's very important that if you consider nonlinear properties of material, including such material as total strain crack, you have to avoid stress concentrations due to boundary and load applying effect. In this case, you should do the same as usually during the laboratory test. Consider layers between boundaries. These layers will lighten the force and reaction transfer and will not affect the numerical solution. In this model, the layers have a lower stiffness against the concrete material. I used elastic material properties for the layers with a model of elasticity of wood. Also, load is applied as a specified displacement at the middle of the beam. That will be similar to concentrated load, but at the same time, I can control total beam deflection. Also, as it's only a half of the model, I used the symmetry boundaries and roller support. Okay, and now as a last step before analysis. On this slide, you can see the analysis properties. Here, I consider only material nonlinearity because beam has simple bending and no need to consider geometry nonlinearity. Typically, for iterative analysis for the most concrete structures, the Newton-Raphson method can be used. For this method, the number of load steps was chosen as 80. Because in my case, I will build a load displacement curve, and to have this curve quite smooth, I need a lot of points or steps. The maximum number of iteration is 200, but program will consider only the necessary number of iteration based on the convergence. If to talk about the convergence, it's preferred to use energy and force known with the values that you can see on the slide. And it's very important if you want to build a load displacement curve, or if you want to check results in intermediate steps, you have to save results at each analysis step. Okay, now I would like to explain results for you. The first result that should be considered are strains in concrete. Here are a set of strain types like normal strain, shear strain, Midas strain, and principal strains. Because concrete is an isotropic material, it's better to check tension and compression, tensile and compressive principal strains. They allow you to see the crack pattern in zones where the biggest tension strains. Values of strains also allow you to see what is the current state of defined element in tension or compression softening diagram of the total strain crack model. Then you may check stresses in concrete. In a program, you can define a set of stress points and with a value displaying them on the model. And you can also generate a table of the values and copy them into Excel sheet. This allows you, for example, to build a stress diagram for concrete compression zone in different sections. Stress and strains check reinforcement. Here you can see, does enforcement have plasticity or not? Also, stress check allows you to see, is reinforcement bar works between cracks. You can roughly estimate the crack spacing here. You can check the strains in bars as well, and you can compare the strain with a limited strain. So when you do the check of limited state of your concrete structure, you don't have to check only concrete behavior and check strain and stresses in concrete. You also have to check strains in reinforcement because it could reach a limited. Element status. These results give you a history of element behaviors through the steps. The status results divided into plasticity and the crack status. If to select the plasticity, program shows elements in which stress are reached tensile or compressive strengths, or strains that are in softening zone. As for the crack, here's a quite rich set of results. According to the nonlinear iterative analysis, at each step, find element status is updated. At different steps, element can be loaded. Then in another step, it can be unloaded, then loaded again. And here you can also see, was the crack fully open or not. Crack pattern status. This all are for serviceability limit state. Here you can check stress, strain, and crack widths in a cracked elements. The most interesting result, of course, is crack width, so you can check it here. And also here you can see a crack orientation based on the principal strains. And on this slide, you can see a comparison of ultimate load obtained from Midas FEA solution and experimental test. you can see a difference between rotating crack model and fixed crack model with a constant rotation factor. It's obvious that the results with a fixed crack model are in good agreement with experimental test. And now I would like to go through the working example. I will show you all the main steps in Midas FEA, how to create a model, how to create a reinforced concrete structure. And as for example, I will use a bridge pier cap, as you can see on the slide. Usually when you design a bridge, at the beginning you can consider only a bridge superstructure model with the dead loads and moving loads. From this superstructure model, you obtain reaction at main girdle supports. And then you can create a separate model of bridge pier and apply this reaction at bearing pads. So this example will demonstrate the last step. I will consider 2D model, which includes a bridge cap with reinforcement frame inside the cap, with the bearing pads and parts of the columns. For pier, I used concrete with compressor strength 35 MPa, and for reinforcement, use Class A and Class B. The easiest way to begin modeling is start with AutoCAD. Almost everyone who works with structural design works with AutoCAD as well, and this tool is quite convenient for creating initial parameters of the model. In AutoCAD, you can draw a contour of your cap. You can draw reinforcement, pads, columns, just using simple lines, and then you can save this model in an .exe file. Before import this model in Midas FEA, you have to check units. If you work with millimeters in AutoCAD, you have to select here millimeters as well, and then you can start import. To import, I go to File, Import, DXF2D, and selecting the DXF file. So here's a preview of models that will be imported, and I click OK. To check the dimension, you can go to Geometry, Measure, Distance, and check the size. Okay, next step is create faces from the lines. For this, I go to the surface and plane face feature. I'm selecting lines, for example, of boring pad, and click apply. So this is my ready face. I do the same for other parts. Okay, next step is sew these faces. I need to do this for correct meshing between the parts. So for this, I'm using sew surface feature and selecting all the parts. And click apply. Okay, now I have a group of my parts. Next step is materials. For this, I go to Analysis and Material. In my model, I will have 4 types of materials. One is concrete with the nonlinear properties for bridge pure cap. Then concrete with elastic properties for pads and for columns, because I do not consider these parts, I consider only cap. Then elastoplastic material properties for reinforcing steel with the class A and with the class B. For this, I create the first material. I give a name of material. Then model of elasticity. Poisson's ratio. If you will apply a cell weight, or you're working with a dynamic analysis, you have to also define the density. And constitutive model is a total strain crack model. Here's a fixed crack, second stiffness, then tension function will be exponential, the name of function. Here's a tensile strength, fracture energy, and the crack band width. For cap, I will use element size 100 millimeters. Compression function, I will use a Torrenfeld model. Compressive strength is 35 and 5. And as for shear, I will use constant with a small value for beta factor. And from drop-down list, I will just select the names of functions and click apply. So the first material is ready. The second material is elastic. Concrete properties. Here I will use constitutive model elastic. Other parameters the same. Click apply. And now reinforcement class A. And model type is von Midas plasticity. And here I just apply the yield stress. It's 400 MPa. And class B. Okay, my materials are ready now. Properties for finite elements. Here I will have two type of finite elements. Is a plane stress for concrete and truss elements for reinforcement. I go to analysis property and create first material, first property 2D and plane stress. First is a cap. This group of finite elements will have material concrete nonlinearity, and the thickness is a width of cap 600 millimeters. Click apply. Then pads. I use elastic material and columns. The same data. As for reinforcement, it's not just a simple 1D element, it's a reinforcement element because it's an embedded truss element. I go to reinforcement. As for reinforcement, I have different diameters here. have for stirrups diameter 8 millimeters, for side bars 12, and for main bars and bent up bars 25 millimeters. So I will have here 3 types of material property. So first is D8. It's a section name and section properties. I'm selecting class A and the cross area of truss element. So it's a sum of areas in transfer direction. And here I'm selecting reinforcement. Okay, I have bar section and here's the bar properties. I do the same for T12. And for D25. Okay, it's ready. The next step is meshing. First of all, I'll generate mesh for concrete. For this, I will go to mesh, up mesh, and face. Here I'm selecting a cap face. Element size will be 100 millimeters. Properties cap, and I will consider nonlinear shape function for this element. So I'll add its side nodes here. And the name of mesh is a cap. I can see a preview of my mesh size. Looks good, and I click apply. Next is a mesh for pets. I will increase the size. There's a pets, name pets mesh. Click apply. So you can see because of I use a fuse of faces, and with a different mesh size, I have convergence here. And I do the same for columns. So I'm selecting property columns. And click apply. The next step is the meshing for reinforcement. So I go to mesh, up mesh, and edge. For convenience, I will hide the mesh of concrete and will leave just the lines of reinforcement. It will be easy to select the bar and apply properties. So here in the tree menu, I will hide all mesh. And I will hide reinforcement geometry of concrete. So now I'm ready to work with reinforcement. I go to mesh, out mesh, and edge. Here I'm selecting length of mesh. It will be 100 millimeters. Then I am selecting that it will be reinforcement in bar in a plane stress. First of all, I will apply properties for stirrups. So I'm selecting here property D8. Here's the name of mesh D8 as well. And I'm selecting my stirrups. I check preview. Looks good, and I click apply. Now sidebars. I selected sidebars. Mesh size will be the same. Here's the properties D12. Name D12. Preview and click apply. And main bars. D25. Preview and OK. Okay, I finished meshing. The next step is boundaries and loads. As for the boundaries, I will use a fixed boundaries at the tips of columns. I go to analysis, boundaries, constraint. There's a name of boundaries, just PC. Fix it, and I'm selecting all the nodes. And click apply. As for the loads, I will apply nodal nodes, vertical nodal loads at top of print pads. For this, I'll go to analysis, load, and force. Here's a name. It's done, and the last step before analysis is analysis settings. So I go to analysis case. Here I give name of my analysis. It's a bridge peer. Analysis type is a static nonlinear. Here I will show the program that I'm going to activate in my analysis case, all the mesh elements, all boundaries and all loads. Then for output control, if you're working with a total strain crack, you have to check crack strain and crack stresses. And in analysis control, there's a material nonlinear analysis. You can Rawson. You can add, for this model, you can add 20 number of load steps. This number of load steps is also enough to build load displacement curve here. And the number of iteration, so it is enough. Energy and force criteria. And save all steps. And it's ready just to perform the analysis. In this webinar, I won't waste time for this. So I just make presentation for you how to create this model. And in previous example, I explained how to read the results. So it's enough, I guess. Okay, and now I would like to show you some of the users' examples where Midas FEA was used in design and research practice. So here was on the slide, you can see investigation of cracking of bridge abutment due to the shrinkage and temperature variation during the construction process. This bridge was constructed in China. And using Midas FEA software, engineer created abutment 3D model of abutment with reinforcement inside. He used total strain crack model, and he also used a rotating crack model in this case. And this allowed him to predict the vertical cracks in the cap. And after this investigation, he concluded that the crack occurrence was because of quite complex interaction between the pile cap and the back wall. Here was performed numerical research of shear behavior of reinforced concrete beams that are simply supported and connected to columns in case of frame system. Here user created several 3D models. He investigated them very well, and he created compression. He used total strain crack model with a fixed crack, and as for the compression, he used a torn fill model, and as for tension, he used exponential Hordick softening model. For shear retention, he used trilinear stress shear strain diagram, and this model in Midas FEA allowed him to correctly predict the shear failure and location of cracks. You can see it from the comparison with experimental test on the slide. In this work was investigated capacity to progressive collapse of reinforced concrete frames subjected to different damage cases. Here Midas FEA was used to consider 3D models with a push-down loading. And numerical response of the structure was compared with the experimental test as well. And for concrete compression, the user used torn-filled model. And for tension, he used the exponential Hordick softening model. This project is about designing a coupling joint of prestressed concrete bridge in construction stage. Midas FEA here used for investigation of coupling joint failure based on 3D modeling. Here user used total strain crack model for concrete. He used Turnfield model, Turnfield softening for compression, and multilinear softening for tension. User in this model considered many actions like creep, shrinkage, heat of hydration, and prestressing. And this combination of all of these actions allowed him to predict the longitudinal cracks at joints. This is a research project. Here was investigated influence of transverse steel reinforcement on prediction of cracking in concrete walls and slabs. Research was based on numerical and experimental tests, and using Midas FEA, user created different 3D models. He used solid elements for both for concrete and for reinforcement, and he also used the interface element between concrete and reinforcement. For modeling of crack, he used total strain model with a fixed crack. And as for shear reduction, he used a beta factor with a factor 0.25. And Midas FEA allowed him predict crack pattern in the wall. This is a research project as well, with investigation of punch and shear failure at the edge supported slab. With Midas FEA, user made many comparisons between finite element models. He considered shell model, he considered 3D model. He used total strain crack model as well with a fixed crack, cracking, and for concrete, he used exponential tension softening and parabolic compression for concrete compression. And as for shear retention factor, he used 0.3 beta factor. And this numerical research showed very good agreement with slab failure with experimental test. This is design project. This project of multi-story building. And this work was performed detailed investigation of suitable reinforcement arrangement in beam with web openings. Analysis by user was performed in 2 stages. Firstly, he created a global finite element model of the building, and he investigated forces that are acting on the beam. And then he created detailed 3D model. And this detailed simulation of beam in Midas FEA allowed him to reduce the original amount of reinforcement and openings that he obtained from analytical formulas. The current structure is under construction. And the last example is about design of prestressed concrete bridge with the complex shapes. Usually when engineer performs finite element analysis of bridges, he works with quite simple beam models. But in particular case, where exists quite complex shape of girder, to use a beam theory is not enough for designing. And here user created 3D solid model of bridge girder with embedded tendons inside. This allowed him in Midas FEA consider real behavior of bridges with different load actions. Okay, actually, this is all that I want to show you in this webinar. I hope it was interesting and useful for you. So thank you all. And if you have any technical questions, you can ask me in the chat window. And also you can later after this webinar, you can write your technical questions on this email, info@midasit.com. Okay, I can see questions. Now I will read the question and answer. So, is Midas FEA compatible with Midas Civil? Can you begin your model in Civil and then pull it into FEA? So Midas Civil generally is used for designing of bridges, of regular bridges in most cases. So when you are working with a simple beam or quite complex beam models with a combination of beam and shell elements. But when you have a deal with a quite not regular structure where you need to consider a quite complex 3D model with the use of 3D solid elements or a big number of shell elements, when you investigate the detailed behavior of some joints, concrete joints, steel joints, it's preferable to use Midas FEA because Midas FEA has appropriate features for working with the CAD models, for working with the complex meshing, with a complex algorithm and computing speed as well. And total strain crack model exists in a full functionality exists only in Midas FEA. But of course, you can create, you can start create your model in Midas Civil. Then you can save this model as a MCT file, is a TXT file with all properties of your Midas Civil model, and you can import this model in Midas FEA, and you can continue work with this model in FEA. So the link between Midas Civil and Midas FEA exists. Can fiber reinforced concrete be modeled with the Midas? Yes, it's possible. So if you are talking about fiber section, you can draw general shape of your section. The section could be meshed by elements. You can apply reinforcement inside, apply stress any stress strain curve, and it can be calculated as a fiber model as well. So the question about how can we apply a nonlinear creep across the length of a section? Regarding to the creep in Midas FEA, you can define a set of creep curves based on the edge of applying load. And if you are working with a 3D model with the solid elements, the strains over the head of the member will be nonlinear, and based on the different nonlinear strains, the creep will be also nonlinear. So if I understood your question correctly, I think it's like this. The question is, why isn't the load modeled as pressure? Actually, it's up to you. When I applied load at green pads, I use a model forces, but I could also apply a pressure load and an element H. It's the same. When you apply the pressure on your element and inside the solver, distributed as a nodal node. force nodal nodes. So it's the same as the pressure you apply, or you apply a distributed nodal forces. So of course you could apply a pressure if it's convenient for you. Can we use for plain concrete structures without reinforcement? Yes, it's possible. You can consider your FEA model with only total strain cracked material without any reinforcement, and you can consider this model inside. How can we get the pre-stress tendon losses? Midas FEA has the same features as Midas Civil, if you're familiar with. So when you apply tendon inside the model, and when you calculate this model, when you calculate stress deformed state, you receive deformation of your tendon, and Midas here use formulas based on Euro code, based on ASHTA code, based on different codes. Midas FEA and Midas Civil use formulas to calculate these losses, and you can check these forces inside the software. Is it possible to see the crack width? Yes, it's possible. Let me go back to the slide with the crack width results. It's here. So the crack width is in element crack pattern, and here's the normal crack width. This value you will see in the legend after analysis. What if we don't sew faces and give aftermesh option? So the idea of sew is next. For example, I have separate faces here, and for this cap, I would like to use very good mesh with very small size of elements, because I investigate this part of model. But for other parts, I don't need quite good mesh. I can use a coarse mesh. But when you use aftermesh at the edge of your face, you will use the size as you used inside, and it will be, for example, 100 millimeters. And here you will use mesh size like 150 or 200 millimeters, and you will get this convergence. So you in this case, you can't calculate this model. Sew of faces gives you convergence or not. So you will be sure that convergence will be. The question is, what if I model the load as displacement? I don't understand this question. Could you please describe it more details? You can apply Excel load, or you can apply displacement, and that will give you same results if you do it correctly. Okay, I think I answered to no questions, and I do not see any more questions. Thank you all for watching and listening to this webinar. If you will have some other questions later, just write by mail. Thank you all, and goodbye.